So welcome to today's workshop, practical industry use case, applying hybrid and graph models to explain AI decisions. Before we begin, I think we have about 2 hours, but at any moment, please feel free to interrupt me and ask any doubts you may have. Um, I'll actually be glad to know you're following along. And since it's not an easy topic, more reason to do so. So what will we do in this presentation? First, we will start by introducing myself, XAI, what is XAI, and as a way to tell you about the context around this presentation, and a way for anyone who hasn't heard much about XAI to tag along. Then we will, next on step number 2, we will move to hybrid models, XAI's central structure to ensure XAI-ready models are possible in any use case. Given the topic of this presentation, I won't talk much about the actual models, but instead I will focus more on the XAI tools. However, if you want me to expand on anything, again, please let me know. Next, we will have XAI through GraphML models, which on the other side focuses more on graph machine learning rather than XAI. I will explain this more in depth, but there's just not that much on graph machine learning, so I will focus more on this technology, which I think is actually really great. We will get into a 5-minute breaks for everyone to refill their coffees. And after a short break, we will talk about some approximation of a real industrial case. We will take an example on the automotive industry, and we will talk about how we would handle things and an theoretical project. And we will end with a hands-on where we will run a toy GraphML model on toy data. Okay, before we start, allow me to introduce myself. My name is Ausiàs. I'm a computer scientist specialized on structured data, machine learning, explainability, and GraphML. I work at Tyris AI, a company based in Valencia, in Spain, which works with many companies such as Ford and many others to deliver structured data and visual machine learning with XAI systems for trustworthiness and security. I've worked on this myself, and so what I bring in this presentation, in this workshop, has a lot of what I've learned in these kind of projects. But even though Tyris will present in this workshop, the XAI project goes way further. We are 15 EU-based companies, from developers to demonstrators, tasked via a EU-funded project to research and develop solutions to the hardware to Industry 4.0 and 5.0 standards to resolve the day-to-day problems and optimization opportunities. Each and all of them dedicated to bring explainable artificial intelligence to the manufacturing industry. You may recognize some of these companies, which are the bright minds behind this project, but they are also companies with wildly different use cases, wildly different objectives and working environments. So it's a really multinational, but also really diverse team. But in XAI, our efforts are focused on developing and delivering our platform. This platform is tasked with handling from data ingestion, preprocessing, training, inference, and explainability, all the way to visualization. For example, here we have a use case that very well could be a real one. Here we see some data which has been gathered from some machines stored in a dataset in the platform. The user would train a model and an explainability tool, which together we call hybrid models, to later set up a recurrent inference and explainability pipeline of the newly gathered data to be explained. The user then gets that information to take real action based on the decisions the AI has seen. However, this is not only intended for experts. Different representations of the results can be generated for different skill levels. For example, yes, we might have an expert in one company, but more often than not, we will probably be working with people which are not especially proficient in statistics. So we will also need to have explainability explanations which are directed to them, a simpler, more specific, because they may only want to know ASEAN specific data on their task at hand, and the platform allows this. If you want to check more about the platform, I've also added 2 references and QRs to the main sources of information about the project. Feel free to, if you want, scan any of them. You can get from one to the other, so don't worry, you don't need to scan them both. Now we can start talking about XAI. Currently, there's a high investment on AI research and development. The technology was growing better by the day, but as we all know, the boom of OpenAI technologies are probably even increasing these values further. Our project is part of this research. The EU has granted this project to ease the adaptation of new AI technologies in the manufacturing sector. However, our project is not actually focused on machine learning itself. It is a big part of it, but our project has explainability as its core goal. Because that's what the X stands for, explainability. If I were to ask you, what's this? Don't answer, we'll train a model. Okay? We train a model and we get a prediction that, oh, it's in fact a cat. Great. Or is it? We can easily verify this is a cat. We can see the picture, we have seen many cats before, and we can recognize this in the image, but this is not always the case. In real life scenarios, we might have tons of data gathered from many different sources, for example, many machines, each with their own data, where we need to predict something along the ways of will they break, will they produce enough, which are not easy to, is not easy for a human to understand how the factors, which may be easily in the thousands, affect each other to bring to this output. Also, the decisions are not mislabeling a picture of a cat. They may cost real money. We can just train a model and put it anywhere and call it a day. We need to transmit this information. We need to transmit the results, but also we need to ensure trustworthiness to the users that are using our tools. Because yes, the model gives you a prediction, but this is actually a partial picture of all the process. You don't have the insights on the decision. Prediction, which may be the most clear prediction ever, can lead to confusion, lead to the lack of context and communication, because in the worst scenario, it can lead to bad decisions which can cause financial problems or anything. Explainability aims to tackle this. Explainability aims to bring the whole picture to the user, which may or may not decide to trust the model. For example, in edge cases, in this example, we see that enabling explainability has revealed that, in fact, we didn't have hello world, but some random words, which, if taken a decision from that could have led to a bad decision. As a matter of fact, XAI can also lead to better, safer, and more fair models, thanks to the insights also given to the developers. As we've seen, it helps the user by answering the questions that may arise to it on its prediction, like why did you do that, why not something else, when did you succeed, when did you fail, when can I trust you. A regular model may leave the user thinking if it has worked properly, or this is an edge case, was this reflected on the dataset, have I changed something? Because yes, a result of this is a cat with a probability of 93%, well, probably it's a cat, but if your company depends on it, might not be the best idea to take hard decisions on the behalf of a model. So we have explainability, and yeah, we predict this is a cat, but also we predict that we also give the user that this is a cat because it has fur, it has whiskers, it has claws, it has ears, cat ears. It has a set of features we can correlate with a cat. So in the worst case where it has labeled a cat a lion, maybe we see that it had the fur is too big. We can understand that the model has failed. The model has provided the why. The user can know when the model will succeed, when will it fail, because if a very confident prediction is given by the wrong reasons, an expert user can, which may see something weird, can verify this to ensure that the decision taken is the best one possible. On strict terms, XAI is a methodology with the goal of bringing understandability on the decisions that the models do. In here we have interpretability and explainability as part of the explainable artificial intelligence, but actually it has a lot more into it. But these two are the core ones. But why does explainable AI matter? Artificial intelligence systems are performing tasks previously performed by humans. We all know AI is a great tool with great promises, but we need trust in order to be able to grasp its full potential. If the model goes wrong, sometimes we can't put it on the most critical processes. We may not even put it on less critical ones, if that might be that may leave us with problems. Sometimes the human will go wrong. Sometimes the model will be wrong. But a second opinion is never something bad. If a human takes a wrong decision and the model takes the good one, then when there's these different decisions, the human can take a closer look and see if the model failed or it was his or her own fault. This is why the XAI is so important. It addresses the need to interpret a machine learning model and explain the thought process of the model in order to grant this very much required trustworthiness. Because as we've seen, a black box model may create confusion. To the business owner, it can lead to doubts about trustworthiness on the models. The IT can have different can have problems monitoring the model. The data scientists can't be sure it's the best model. Yes, we have loss functions, but this goes further, because on edge cases, bad decisions taken by the wrong reasons can lead to poor decisions. But they not only can be used to ensure proper functionalities, but they can also be beneficial for every layer. For a data scientist, we can increase the understanding in our model. We can improve its performance. We can create better algorithms based on the decision. If a decision was taken which we didn't expect, we didn't account for, maybe there's some other architecture which can better grasp this relationship. For a data analyst, it can find bias and transparency of the model. I have added an example later, the next transparency, the next slide, which, for example, is about the Boston housing, which is biased. The data analyst can also understand the impact that this can have. Maybe there's only one wrong decision, but it's a really wrong decision. And the user can also increase the trust. And if it's a really good model with really good promises, this increased trust can mean the difference between trusting it only in the lesser important stuff and the most important stuff, where it can bring actually an advantage. But we could add the example of a person which requested a loan and the bank rejects it due to a model's prediction. Okay, this model was trained using the Boston housing dataset, which is infamous for its lack of fairness and in racial terms. However, when the customer asks for a reason behind the rejection, nobody can actually give her an answer. Where this be tackled by a human, the user could, the one requesting the loan could receive an answer why or why not this loan was provided, and the user could verify if this is actually a bad decision. But this is an example for a loan. Imagine, for example, a more extreme medical case where a model predicts whether you require or not surgery. You'd rather for you and your doctor to know the reasons behind a decision instead of, for example, I chose randomly this decision because this data was unusual in my training dataset, which can happen. Explainability can call injustice and benefit everyone by allowing the loan. Since explainability raised the flag, the human took a closer look and better evaluated the case. This increased the robustness of the decisions of the model, which increased the stability, which provided fairness, which was needed for the responsibility related to the model, which verified the transparency of the model, which is required for the interactivity, which enriches the interpretability and validates the explainability. All of these, all the way around, increasing the trustworthiness of the model, both from the customer point of view and also from the company point of view. Alone, again, might not be the most extreme of cases, but as long as AI keeps getting inside all parts of our society and improving it, we will need more and more explainability, since not all scenarios a bad decision can impact can be so low. For example, in this figure, we can see that, yes, in the customer side, well, a book recommendation, ad placement may not be critical, but if we go up on the chart, we see that smart weapons, cyber threat detection, self-driving vehicles, medical diagnosis, fraud detection, those are really important parts that we need for our society to work well. We can't allow a self-driving vehicle to be working bad just because an issue on the dataset which could be prevented by explainability. Now we're going to talk a bit more about hybrid models. As we've mentioned before, our hybrid models are core in the design of the XAI platform. They are comprised by any machine learning model which is guaranteed to work with an explainability tool. This is the case for our hybrid models in the XAI platform. Since we can ensure this, the end user can decide whether to use it if it's of value for themselves. So, okay, a hybrid model is a machine learning model which will have an explainability tool available to explain direction, but what XAI tools do we have available? Explainable AI varies a lot. The research is ever expanding. It's something rather new. And so there is not like a common format of explainability tools. The different techniques come in wildly different formats and wildly different explanations, but we can classify them in some groups. For example, our first group here, the simplest one, are the interpretable models. Interpretable models are the most basic of XAI techniques. They imply that the model you make must take into account explainability or be simple enough that you can explain the results just with the base model. For example, models such as decision trees are self-explanatory because they contain all paths required to explain the results. Each ramification of the tree is a condition, so by backtracking the path taken to reach the final leaf node, one can see the decision process of a sample. If, for example, this decision tree was a classification 1, we could take all leaves that get to a class we are interested in, and by backtracking these leaves, we can see what conditions get us to those classes. Another simple example is, for example, linear regression, where the formula is simple enough that we can, just by multiplying the weight and adding the bias to a given feature, we can get a result, thus explaining why the result was the result of the input features. The second group are the post-hoc model agnostic XAI tools, which are designed to work with roughly any model. These, which grants a lot of flexibility to the developers working with them, limit the way the tool can work. In fact, most of them usually work by permutation of the input features, because there's not much you can affect if you don't know what's inside the model. Model agnostic models can work with dense neural networks, deep neural networks, attention layers, convolutional networks, and also classic models, which, for example, linear regression or random forest. Next group is the post-hoc model-specific models. They depend on the model which are used. So one technique used for one type of model may not work with any other, but they can get interesting explanations because we are taking into account the way the model works. For example, we can see here GradCam, which is like the attention, the input, the scores, the importance of each feature, in this case a pixel, that the model takes from the input image to the output. No, if in this case if we are seeing a bird, we see that the model does not take importance on the sky, but in fact does it on the silhouette of the bird and the branch. Other techniques such as LRP may backtrack the weights of the model in order to get to an input from an output, thus explaining this output. The model-specific models can also be designed to be specific. Sorry, explainable. Another way of classifying these tools, which is also very interesting, is global and local explainability tools, which is a way of seeing what you want to explain. Global XAI tools explain relationships over an entire data set. So they are more generalized. They are heavily dependent on the available sample. So a biased data set will probably bring bad explanations. So it's really important to verify the data given to a global explainability tool. Local explainability tools, on the other hand, explain one given sample. So this is more useful usually because usually the data you receive the data and you want to make an explanation for it. So what you are actually explaining is a sample. So you are probably using a local explainability tool, which is giving you the insights on the decision for that given sample. However, usually both use a data set, a sample of data, in order to give context to the relationships that are extracted from even the given sample. For further reading, I've also added two QR codes, which I think are interesting. On the left side, we have principles and practice of explainable machine learning, which is like an article which has a lot of insights on all that we've talked. Also, has this way of classifying the models and goes a bit more in depth. On the other hand, Hybrid XAI is a library, a Python library, which also brings like explanations and the original documents of the research that created the explainability tools that they have available. There are more Python libraries other than Alibi, but I like this one because it's been some time already, and the way they bring the information to the user is great. Great source for learning more. Okay, we can go now to XAI through GraphML models. Again, we will talk more about GraphML rather than explainability. But because explainability on GraphML models exists, I've used it, worked great, but it's not as extensive as on regular models, and sometimes requires some tinkering. So I will focus more about how we learn to use GraphML models and how they work, because they are a bit hard. And this was part of our research in the platform. So I think it's good to bring here this. I will tackle the first and easiest misconception of all people learning GraphML that might have had at first glance. If you have ever researched or think about GraphML models, it happened to me. What I thought was I would have an adjacency matrix and data linked to that adjacency matrix. But GraphML models are in fact not adjacency matrices. Adjacency matrices are not easy to make extensible. On the other hand, GraphML is. If I were to train a machine learning model with rugged tensors for adjacency matrix based model, I would require a lot of structure on the data, which is a lot of overhead, which is not easy and not fun. So yeah, GraphML are not adjacency matrices. GraphML are comprised of three parts. They are the nodes, the edges, and the context. Nodes are like entities of data, edges connect those entities, and the context is global across all the graph. For example, in this example, we see here a small little graph where we see what could be like a few streets of a city. With intersections, we see a park in the middle, a shop, a major town, a bus stop, and a few roads, right? In this case, we could have like a park with information about the park, and shops with information about the shops, the bus stops with information about how many citizens go in and out on this stop. And this could be used to make predictions on the actual graph. What may affect these predictions? Well, the temperature of today, the weather, or whether today is holidays or not. But seeing this, question may have arose to you. Isn't this a regular graph or a regular network? Can we just represent this as an emergency matrix the way we would do if we were to actually make computations on graph theory? I won't get into the details of designing GraphML, a GraphML counterpart using complicated ML. It might be possible, but it's really hard. Instead, GraphML brings this to us, allows us to create different nodes, different relationships between the nodes, and gives us a way to learn from it. The difference with a regular graph lies in that we will have different kinds of nodes and edges. We have an heterogeneous graph, it's called. The graph will make use of our expert knowledge in order to connect only the information that is relevant to each other. Because probably having a park near public transport implies that more people are likely to go to that park. However, let's say that one of the stores is actually a liquor store. Will there be a correlation between that store and the town hall? Probably not. So we could add a relationship between the park and the bus stop, but we could not add a relationship between the shop and the town hall. In fact, GraphML, the way it works is by updating the graph. The way we update a graph is sending the information from, for example, from one node to its neighbor nodes, right? For example, we could have in the park, how many people are in the park? Well, we send the information to the nodes, and we update those nodes. So the people which is in the park at any point will probably live through one of the four available roads, and that people will be in one of the four intersections. If we update the graph even more, we will bring more information to all parts of the graph, thus making it more accurate if that's what we want to predict. However, the graph we have on the right side is not a fully connected graph. Why? Well, as I've mentioned before, GraphML uses our expert knowledge to trim unnecessary connections. This also allows for easy implementation of multiple independent data sources more easily. In this case, we could have the information of a node in an edge, the information of a shop, as a node of type shop, the information of a bus stop in a node of type bus stop, and the information of the town hall. In regular machine learning, probably we would have to create some sort of complicated architecture or concatenate all the data, thus giving the same importance to the relationship between all the features. But in fact, we know that probably the shop does not affect the town hall. So why connect the town hall to the shop? We can connect the shop to the park. We can connect the bus stop to the shop and to the park, and the town hall to the bus stop and to the park. This way, we can save resources and training time. But why would you use graph machine learning? Well, what's this? This is a map of air routes around the world. This is the path from airport to airport that airplanes take. Doesn't it look familiar to similar to a graph? This is a map of a city. Doesn't it look like a graph as well? This is the floor of a building. It can be represented as a graph. And finally, social networks, the network of the employees of one company can also be represented as a graph. For example, based on what projects are they on, what people they talk to more, etc. Graphs are roughly everywhere. They are an easy representation of data, and GraphML allows us to get the full potential by integrating graph theory with machine learning in order to learn to move information through the graph in order to make predictions. Since graph neural networks work very well, very similar to deep neural networks, explainability is actually rather similar to the aforementioned techniques applied to regular graph deep neural networks. In this case, for example, this is a real use case. This is a graph model trained on some data, some real data, where we see the flow of information in the form of the arrows and the attention scores, because this is using graph attention. We see in color, the brighter the color, the more important it is for the prediction that we made. So, for example, if we see very bright green nodes, very bright red nodes, they are affecting very much to the output. So we should take a look what's happening in them. For our AI automotive use cases, we could see the difference between using a regular AI pipeline versus using XAI. We will start the same way with an ETL, which in the case of XAI is integrated. And we could get some sampling, featuring, and create a machine learning model as a black box, which, as we've seen many times, as I've said many times before, reports, for example, a drop in the number of manufactured goods. But why did that happen, right? In XAI, we actually get a more informed and better understanding of the most impactful factors, so an expert user can actually understand why the drop in the number of manufacturing goods happened and can fix the issue. So let's put more a more specific example, a potential user has a manufacturing line. For example, the automotive case we started talking about before. Different machines are used for the manufacturing of different parts. In the process, they wear down. Some components need to be replaced after some time. This is understandable, but they break. They cost money. They cost production time. They produce delays. So once they happen, you must stop the entire line. You must take some knowledgeable individual to fix the machine, which may or may not be easy. Instead, we can use Explainable Platform to get a system capable of detecting future bottlenecks and get the reason. Since we know when the bottleneck will happen, where the bottleneck will happen, and the reason behind it, we can actually schedule predictive maintenance, optimizing the uptime and the delays caused by the wearing down of the machines, thus keeping the line running. However, these issues will be dependent on what parts are we manufacturing and in which order. So we could also get this information in order to also optimize the order of the parts which are manufactured. For example, we could theorize two different schedules and predict when the machines will fail. Based on these schedules, the end use case can decide, based on their expert knowledge, what schedule fits better with the maintenance breaks, and maybe even make it before the actual machine breaks.